excited to have an in-person and hybrid Research Connection speaker series today. The Research Connection speaker series is an opportunity to highlight the relationships being built across the research organization and showcase some of the exciting work that's happening in the industries that Autodesk serves. If you know of an external speaker that you think our research community should hear from, please reach out to me and invite them to participate. And I'll also post a link in the chat for a form you can fill out for the folks that are online. Now, we have a special presentation today. Gil Sunshine, who's been with us as a resident for a long time under the team Duality, which is upstairs. They're doing all the reality capture stuff in the tent that you might have seen if you're in person here. They build a model that takes advantage of really high fidelity technology in Unreal Engine and their own platform to train AI models on synthetic data. So check them out if you want to learn more. But today, Gil is going to be sharing his related thesis work from his time at MIT as he pursued a Master of Architecture. So with that, I'm going to hand it over to Gil for his presentation. We're going to have a Q&A at the end. So for anyone online, please submit questions there. And then we'll also be able to pass the mic around here if there are any questions in the room. Thank you very much. Let's give Gil a round of applause.
Is this on? You hear me? Yeah, okay. Thanks for coming to everyone here and online. So yeah, I'm going to present a project that attempts to reimagine CAD software to be more aligned with ideas around circular construction. And one of the underlying arguments here is that if we're going to talk about sustainability in design, then among other things we ought to be looking at are the tools that designers use, which today primarily comes in the form of software. So hopefully if you work on CAD or if you're just a user of CAD, this will be relevant to you for that reason. And as Gabby mentioned, the work was developed in the context of an architecture thesis. So I will be talking about architecture specifically to some extent, but the ideas are sort of relevant to design at any scale where you're dealing with materials and geometry. All right. Oh, yeah, I can move it forward. Extrude, saw, turn, repeat. During the Industrial Revolution, machines and techniques were invented and advanced for forming materials into standardized shapes. This would lead to the development of the industrially mass-produced standardized building materials used today and left an indelible mark on architectural thought. The architecture of modernism, especially the international style, embodied the logic and efficiency of the factory, while the endless linear and rotational processes of industrial production were quite literally imprinted on its geometries. To an unprecedented degree, architecture became a practice of blind trust in superficially dimensioned materials, meaning standardized materials, specified from afar. Extrude, trim, revolve, array. This intertwining of mass manufacturing and architecture has only intensified over time, finding its way into the tools of the architect. The 3D modeling software used by the architect and designers more generally contains analogues to the machine processes and abundances of industrial production. By instantiating geometry that was not there before, with minimal apparent effort or cost, such software obscures the extraction, processing, transportation, and waste necessary to physically realize said geometry, and suggests that the only limit on the material world is computer processing power and memory. This poses a challenge as it becomes increasingly apparent that circular approaches are key to minimizing the deleterious environmental impacts of construction, both in terms of greenhouse gas emissions and waste. Given architecture's proclivity towards the standard, how might these increasingly urgent pressures make their own mark on architectural thought and design? Rather than operating solely with the mindset of material predictability under an industrialized global supply chain, architects and designers must also learn to accommodate materials as they come. In order to adapt to material irregularities, which are inherent to a non-standard material palette, various 3D scanning techniques have been adopted to produce digital representations of materials, which can then be manipulated in 3D modeling software to derive digitally informed fabrication and assembly processes. By the nature of their discrete sampling, however, these representations vary in their precision. What the designer encounters in the 3D modeling software is not the material itself in its infinite specificities with its weight, its moisture content, and smell, but rather a surface representation, or a mesh, composed of a large but finite set of points. These representations inhabit the space between the low resolution of pure geometric abstraction and the high resolution of physical phenomena, and therefore might be called medium resolution. If there exists a deeply ingrained connection between 3D modeling software used by the architect and the processes of industrial mass production, then in order to overcome the cognitive grasp of the standardized material palette, the 3D modeling software itself must be reconsidered. In general, 3D modeling software allows the designer to create and then alter a geometric representation. Though the geometry in a 3D modeling environment always references future actions and energy inputs upon construction, shape itself does not suggest process. Digitally, a sphere Boolean from a cube suggests a process of removal. Physically, this shape might be fabricated using an additive process, like 3D printing. As I demonstrated a couple slides ago, in CAD software, we often operate through analogy, constructing geometry with digital operations that reference physical ways of making. But generally speaking, we rely on the contextual understanding of the designer or feedback from simulations to implement those operations in logical ways as far as manufacturing and fabrication are concerned. The research I'm presenting offers an alternative to contemporary CAD software, where the gap between digital models and physical constraints is vast. Rather than abstract commands that project forth a not yet existing material condition, the software I'll be presenting, which is called Inventory, is based on digital representations of materials and processes from the physical world. Inventory is CAD for this medium resolution paradigm. This is the inventory interface. It gives the user access to 4 sub-inventories. These are parts, sites, actions, and protocols. Any given item within one of these inventories can itself be understood as an inventory or a container for information and media. For example, a part from the parts inventory may contain links to videos showing the harvesting and processing of the material. Item panels also contain relevant UI elements for adding parts and sites to the scene or activating actions and protocols. CAD is a virtual space, but is also the place where very real design decisions are made with significant material implications. Construction and production of building materials accounts for 5 to 12% of global carbon emissions, and in some sense, we can say that all construction originates in CAD or at least passes through it. This is not to place the blame on CAD, but rather to mark it as a site for productive intervention. By including this archive of the history of a piece of material at the point where that material is specified, inventory attempts to augment the ecological imagination of the designer. Here, materials are no longer anonymous or no longer just geometry. This incarnation of inventory is primarily populated with pieces of split wood from logs sourced on Craigslist, left behind from the felling of trees in Massachusetts. That said, all manner of matter is subject to the medium resolution treatment. Specifically depicted here are short softwood log sections not suitable for use as lumber or particularly good as indoor firewood, and therefore fated to end up in the chipper and left to rot, releasing their carbon to the atmosphere. Minimal processing of the stock through splitting limits material waste and energy input, preserves the structural integrity of the wood's grain, and reduces distortion as the wood dries. Once standard practice for producing all kinds of building materials, from structural members to roofing shakes, wood splitting today has been relegated to firewood production alone. However, the technique finds new relevance in this medium resolution paradigm, where producing planarity through further processing of the stock offers no benefit. Inventory understands the built environment as a temporary configuration of materials in motion. Therefore, processing doesn't increase the value of a piece of material, rather only limits its potential for further use. Stock may be taken up into an assembly one day and returned to the inventory the next. The parts inventory contains representations of specific pieces of material that can be added to the modeling environment. Parts are unique mesh representations imported from the physical environment to the digital using photogrammetry. In inventory, there's no object snapping. Rather, objects collide and settle into one another. There's no coplanarity, only closeness. No aligning to the XY plane, only gravity. Sites are mesh representations of physical locations. In the medium resolution paradigm, there's no distinction between the representation of parts and of sites. Both are meshes. The site is not the place where something is to be built or where materials are to be assembled. Instead, it is understood to be part of the assembly itself. Actions are digital abstractions of physical operations made on parts. Dowel part, for instance, refers to making a hole in a piece of stock using a 6-axis operation in order to receive a dowel. Add wax refers to adding a piece of polycaprolactone wax, a reusable bioplastic, between two pieces of stock. These actions were developed through a series of physical prototypes, an observation of the constraints that pieces of stock, dowels, polycaprolactone wax, and rope put on one another in various configurations in order to join parts. Once physical joining methods were developed, they were abstracted into digital actions. Practically speaking, these actions applied joints to rigid bodies using the Unity physics engine. Pin 2 parts, for example, asks the user to select 2 parts and add a pin, representing a wooden dowel between them. If the z-axis is understood to be along the length of the pin, then once the joint has been activated, it restricts motion between parts in the xy plane and rotation around the x and y axes, but allows rotation around and movement along the z-axis. In order to restrict rotation around the pin, or the z-axis, the user might select the add wax action, which is an abstraction of smushing polycaprolactone wax between parts. The polycaprolactone wax is not an adhesive, but by gripping onto the irregular surface of the stock, restricts rotation between parts. In order to restrict translation along the z-axis and fully constrain the joint, the add ties action could be implemented. First, dowels would be added to each of the pieces of stock, roughly perpendicular to the initial pin, or the z-axis. And ties would be added between them. So this offers just one example of various ways in which several actions can be combined to create fully constrained joints. Like the geometric representations of materials contained within inventory, these digital actions might also be called medium resolution. They are not the actions themselves, but representations that extract their essential function in constraining rigid bodies. And so here we see that modeled joint. And just to make a note about the wax, because it's sort of key here, which is that because these scans are medium resolution, and in the case of this project, they're not super high quality scans, where the surface of a piece of material actually falls is sort of in a range rather than a known value, and so the wax serves to as the interface between parts and kind of soaks up that tolerance. In addition to placing parts one by one, protocols may be used to algorithmically determine patterns of interaction between parts. Parts are assigned anchor points that determine points of attraction, and distance constraints are applied, pulling them together. In these examples, the form of the assembly is determined by the unrelenting drive of the parts to be close to one another. With these protocols, we can see how this project takes advantage of physics simulations at multiple scales. Previously, I showed the modeling of a joint where rigid body collisions and various axial constraints were used to join one part to the next. With the protocols, attraction forces are used to organize many parts. Given a large number of irregular pieces of material, rather than having to place each part one by one and ensure that no piece overlaps the next, rigid body collisions and attraction forces set in motion these animated assemblies, which in some way organize themselves. In addition to attraction forces between parts, sites may also be assigned anchor points, creating site-specific assemblies. Once a given organization has been achieved by a protocol, actions may be used to fix the position of parts relative to one another and the assembly fabricated. The physical actions that were abstracted into inventory can become physically real, now choreographed by the information contained within the software. In this preliminary phase of the research, the geometry modeled in inventory was exported to a secondary set of software tools for robot path planning, but a potential next step for the project would be to integrate those robot controls within inventory in order to more fully realize it as an interface between the designer and the physical world. The goal would be that inventory takes information about pieces of material as an input and outputs information about how to alter that material to build assemblies of parts. So just to briefly describe the fabrication workflow, a somewhat rudimentary clamping end effector was designed that could hold irregularly shaped pieces of wood. Once a piece of wood is attached to the robot arm, a secondary photogrammetry scan is performed in order to understand the location of a piece of wood relative to the robot coordinate system. So this is what you're seeing on the left. So if that red target is at a known location relative to the robot, and if you make a scan that includes that target, then you can coordinate the wood space with the robot space. And as you see on the right, I have a drill press set up in the robot cell. And so the job of the robot was just to accurately position the wood relative to the axis of the drill bit. And then I would go in and manually lower the drill press to make the holes. And drilling was chosen as the main operation to alter parts because it's sort of minimally invasive and extends the reusability of pieces of material. With this workflow in place, a collection of prototypes were developed to explore a range of conditions, starting with a self-supporting column. A second prototype explores the construction of a vault. When there is no longer a need for a given assembly, or if a structural failure occurs, the parts can be returned to the inventory. However, these are no longer the parts in their original state, and embedded with them are the information and scars from their prior use. This information can then be used to drive a future assembly within inventory. For example, the broken components might be removed from the assembly and new connections made based on the intact pin connections. The broken components can then be reintroduced as bracing in this example. What was a vault is reconfigured into a beam. So sort of to wrap up, what the project offers is a proposal for how to design. Inventory composes architecture or architectural elements, at least, through the interaction of parts, sites, actions, and protocols. Each category is made up of digital abstractions of physical phenomena that encode and make apparent their physical impact. Rather than the model-forward practice of design that dominates today, and which is predicated on trust in the availability of standard materials, inventory establishes a dialogue between physical material conditions and digital models. In inventory, design and construction are not a one-way stream of information and materials ending as a file in a computer's trash and a 2x4 in a landfill. It's not that our world should look like these prototypes or be made from these materials in particular. Instead, it is about disentangling ourselves from the standardized material palette and our reliance on the predictable surface, which has become deeply entrenched in both how we design and in wasteful construction practices. Inventory peels back some of the layers of abstraction authored into contemporary CAD software to allow the designer to be more specific and explicit about their interaction with the physical world. As an open-ended platform for design, this research anticipates the expansion of each of the inventories to accommodate a greater diversity of materials or parts, places or sites, fabrication processes or actions, and algorithmic design strategies or protocols. Thanks.
Thanks so much, Gil. It's amazing work that, it has so much of what we talk about within research, from digital twins to synthetic data, CAD representations, and all sorts of really interesting strategies. We're now in the Q&A portion, so if there's anyone that has questions online, send them to the chat and I can ask them for you. Anyone have questions in person here? I have a few, so I can also get us started. All right. So can you talk a little bit about your transition from exploring these themes in academia to exploring them in industry with Duality? Was there a link? Did you find like there was a strong link? Did any of that prepare you for what you would face in, applying this to industry?
Yeah, I think, well, that was like where my interest in working for Duality came from in the first place, was this idea of using digital twins to work on something that is, or like strategies that people are using for entertainment in the metaverse, but applying them to like real building projects, essentially. Duality doesn't work on construction in particular, but sort of like the conceptual underpinnings are similar. Um, and then beyond that, just having worked with photogrammetry a fair amount. That's just been super relevant to what we're doing here specifically. So yeah.
For the people online, could you, and the people that don't know, could you briefly just touch on what your focus is?
Yeah,
at Duality?
so Duality's been, we've developed 2 prototypes here. We built them in the shop. So basically, the it's a machine that does photogrammetry. So we have a turntable and an arm that pivots around the turntable, and you can kind of set a product on the turntable. It's made out of acrylic or glass, so it's see-through, so you can take pictures basically 360 degrees all the way around, and then reconstruct a 3D model. Yeah.
And you created really nice models here of the hardwood. And so what would folks do with the models once they generate the, 3D model of a physical object in the Duality platform?
Oh, so so what we're scanning primarily is consumer packaged goods. So these models will then go into a virtual environment and be used to generate data to train different models. So, for example, you can think of like self-checkout or warehouse automation, that sort of thing, where we can kind of populate a virtual world with tons of these models of consumer packaged goods. Yeah.
Cool. It was pretty impressive what you put together with the inventory platform. Like it was an entire kind of software that could simulate all of this in what looks like some crazy physics and some real world physics. And can you tell, was that direction of the research influenced by your community at MIT? Was it something that you were really interested in, focusing it in?
There's kind of there's sort of like I would say like an aesthetic movement of using physics simulations to do kind of like compositional, it's like using physics as a compositional strategy in architecture. And so this was kind of not a reaction to that, but it's kind of doing that while also sort of trying to take advantage of physics as a tool, either in like direct and obvious ways or kind of in sort of like as a trick to use it to do productive things. So I think the initial like inclination to even work on physics with materials came from this sort of aesthetic movement, but then trying to move beyond that a little bit to sort of use it in a real world setting. Yeah. And there's obvious limitations to it, like that vault collapse and things like that, right? Sort of like the idea I kind of touched upon about if you have like a huge mass of materials and actually you don't want to like optimize the materials away. You want to actually use a lot of materials. Well, in that scenario, it becomes hard to actually place all of the pieces of material in a way that is productive. So you can, just like set up a system where things just kind of, go together in some sense. Yeah.
And you present kind of a provocative new approach to CAD in this research that doesn't just focus on, these simple shapes and building it up, but on kind of like the materials that you're using in the real world. After going through this entire process, has that vision continued to evolve in any way into like how you see that might actually be realized in either industry or, actual products that people use outside of research?
Yeah, I feel like so what I showed is like like kind of the extreme version. And I feel like maybe more of like a hybrid approach is what makes sense, especially. Yeah, I mean, So in a scenario where you don't have just like unlimited access to scans of materials that are going to work for you, well, maybe you need to take a hybrid approach and you're using some off-the-shelf standardized building materials, but then you can kind of sort of maximize the use of recycled materials as much as possible. Yeah.
Cool. Thanks. Last call for any questions from the audience.
Yeah, really cool proposal and presentation. Makes me think about modeling through just manufacturing constraints is just like a really interesting paradigm, and makes you think that we can capture a lot more data about like cost or carbon in a really more direct way when you like are making geometry moves purely on, you know, real world actions.
Mhm.
But it also makes you think that it would be really difficult to make some of the kind of crazy geometries you see in architecture these days.
Mhm.
And so, yeah, I'm curious what kind of like hybrid approaches in terms of form and geometry
Yeah.
you think might stem from being constrained in this way, but also like the benefit of that
Yeah.
in terms of data.
Yeah, I think like part of like one of the underlying arguments is about almost like pumping the brakes on authorship and or maybe saying that this is like a new version of authorship. So yeah, we have all these like crazy shapes in architecture, and they're interesting, and those projects are amazing. But maybe we can also think about alternative approaches where we sort of like de-emphasize or de-emphasize authorship in that way and allow what's available to more be the driving factor in design. Um, yeah.
Yeah, nice.
You mentioned about like process, kind of part of the design tool is like capturing the process. Can you maybe elaborate a little bit more of what are you trying to achieve with that?
Sorry.
Oh, like the process of design. So it's not just a kind of product. My take is it's not just the product of the structure, right? Like casually capture, but some part of the process you think is very important to be surfaced in those tools. Can you maybe elaborate a little bit more? Like, what's your thought around that?
Yeah.
Yeah.
Well, I'm going to answer it. Tell me if I'm not responding to your question. But I think, so yeah, I guess part of the idea is basically to render more explicitly what is the impact of what you're doing when you're designing in CAD. So in this example, like it's very like it's very one-to-one and literal. Like the materials are, I have this piece of material in front of me, and there it is on the screen, and then there's the action. So I've developed these ways of joining pieces of material, and there they are on the screen. And I think that's like too extreme. There, like abstraction is very powerful and important, but this maybe as like a provocation, or again, thinking in terms of hybrid approaches, maybe some ideas from this can be sort of like integrated into existing CAD strategies of trying to make apparent to the designer what happens downstream when they like populate a field of, 100 of the same part, whatever. Yeah, was that? Yeah.
Yeah.
Okay.
I was looking at your software and kind of imagining how it would play out in the real world, and it almost, I think, tell me if I'm kind of on base here, but there's a building in a city. They want to do adaptive reuse. Part of the building is broken, or they want to like modify or adapt or part another part into the building. Maybe it's an old building. The city doesn't want to import materials from all over the world. It wants to use locally sourced materials. And it doesn't want to leave a huge carbon trail by bringing things like from ships halfway around the world. So when you need almost, I mean, looking at this, I'm just sort of imagining the world where this is working. It's like you almost need like a local factory that is scanning all the materials as they come in,
Yeah.
and then that is connected to your software, and then you import those materials and configure it. Is that sort of like the world you're imagining when you make this?
Yeah, sort of like, so there are like examples of um, like material recycling depots, that type of thing. And I guess maybe the piece that's missing is that everything is scanned and there's like this catalog of it. But yeah, I think like maybe a potential like realistic takeaway from this is almost like a Craigslist basically of building materials where there's like a library, things are scanned, you can pull from that library, integrate things into your design. And then I think, yeah, it would be like regional, so you're not like designing with something that's halfway across the world, but totally, yeah.
Yeah, definitely something that's coming out through a number of these questions is kind of a need for a new job profile in order to take advantage of some of these things. And I think at Duality, the fact that you guys, your jobs are, you're making like the portal to digital.
Yeah, exactly.
Is like, how do you get not just like a crummy low poly scan from back in the day, but something that is like physically accurate, the textures are accurate, it can be simulated with the real world physics. So like, yes, this cup is hard, but and this wood is hard, but not all materials behave like that. Some of them change shape. Some of them, you know, light passes through them. And so how do we capture that in our data models? And then whose job is it to then import those so that it can become useful? And then that screw or that piece of wood then has so much more life because it can be integrated into systems that are training models to use it. So, you know, if we had like we have another team in the program like Urban Machine, they're repurposing old lumber, cleaning it up so it can be reused. You know, if that was also scanned and then that custom strange shaped piece of wood could be used in Revit or something else in the design to represent the actual uniqueness and characteristics of the object.
Yeah.
I feel like when drones came out, we had to have drone pilots now at construction sites, and it was like this new job. And so the like synthetic or like digital capture of objects and physical things, I think is
Yeah.
something now you have experience in.
That's my job.
That's your job. Is there anything else that you wanted to leave the group with, or?
No, thanks for the questions. They're great. Yeah.
Yeah, cool. All right. Well, we're going to call it. Thanks, everyone, for tuning into today's Research Connection. Thanks, everyone who's still online. And we'll share the recording on Slack. And Gil's part of the residency, and so are the rest of the Duality team. So please reach out if you have any further questions or ideas.
Thanks.
Thanks, everyone.